Okay, so let us start with forward kinematics of industrial robot. This case, I am specifically covering Yaskawa GP-12 robotic arm, that is an industrial robot, okay, of 12 kg payload, 12 kg payload, mostly used for pick and place. You can mount an arc welding attachment on top of it, and you can do welding operation, painting operation. Okay, so pelletizing task mostly it is used for. Okay, so that is where this robot goes into. Okay, so let us begin. So this is how it look like. This is your standard arm, you see. Okay, so this is your first link. This is attached to the ground. This robot is always attached to the ground with these bolts. If you want, you can see my video which says how it is fixed to the ground. Okay, there is a robotic installation and commissioning. There is a video on that. You can always watch that. So I have fixed this robot to the ground. So this is your 4 bolts. So this link gets permanently fixed. Next link, this link rotates with respect to this ground frame. Okay, and this is your link, this is your first axis, okay, about which it rotates. Okay, then there is a link, this link, this is your first link, this is your 0th link which is fixed to the ground, first link, and then it is your second axis which rotates your second link with respect to link 1. So definitely you can now see this is your frame 1, this is your frame 2, and you have a twist in z axis by 90 degree, right? And then you have another axis which is over here, about which next link is rotating. So this is your third frame, okay, that rotates the third link. Third link is not there where I have marked. Okay, let me just wipe it off. Okay, this is your third link. Okay, and this is your rotation axis, and then whole of this can rotate like this. Okay, so this itself can rotate. So you have another frame which is fourth frame. Okay, I'll mark them much better way now. I'll show you this rotation as a video now. Okay, so this is your fourth link, and then you have an axis which is like this, that can make this rotate like this. So this is your fifth link, and finally you have last rotation, that is your sixth link. So you have 6 links, 6 joints. Okay, and effectively it is grouted to the ground. Any tool will come here. Okay, effectively it may have a point which is here, that is actually working. It is normally run by a controller which is normally YRC 1000 controller for Yaskawa GP-12 robot now. Okay, and a teach pendant. So it looks like this. If you can see it closely, this is a teach pendant where you can do all programming. Okay, you do all programming here. These are key buttons, that is just like a keyboard. This is a touch screen also. These are different mode switches, safety switches and all. So this can be dragged anywhere near to the robot, and you can do all sorts of programming while you stay in the workspace, and you can teach your robot to take it to some place, program your robot. Okay, so this is a teach pendant. This is known as a teach pendant. Okay, so yes. Okay, so let me just show you a quick video of this, how this robot moves in workspace. Okay, let me see if I have that video here. Okay, so this is your first video. Here I go. You see, this is first degrees of freedom. Hope you can see it clearly. This is your second motion, third motion, right? Fourth motion, fifth motion, sixth motion. Clear? Let me just repeat it once again. This is your first motion, correct? This is your second motion. This is your third motion, fourth motion, right? Fifth one and sixth one. Ultimately, it comes to the end effector. Got it? So now going back to my slide. So this is how your industrial robot Yaskawa GP12 is like. Okay, it is a 6 degree of freedom, and you saw end effector. This end effector can be oriented in any manner, and this position can have any position in its workspace. So this is your P, X, P, Y, P, Z, is it not? So that is your position, and this frame will have its own orientation. Okay, so it is your Z6, X6, sixth frame now. So this is X, Y, and Z. So effectively, it will, all these will have NOA projections along global frame, that is X, Y, and Z. Okay, so this is your global frame about which this end effector frame can go. Okay, and it can have any position given by this and orientation given by orientation of this frame. Got it? Now let us assign, let me see more closely these. Okay, so this is your markers. This is known as reference marker. Hope you can see this very clearly. This is your first reference marker. You see this? Is it not? Okay, just a sec. Let me just take another color. Okay, so this is your marker, which actually says, okay, now it is at 0 degree. Now it is at 0 degree. Okay, you can move it. Let me see if I have a video for this. Okay, so let me just move it. Okay, so this video shows how it can move. Yes, so it is moving at a positive direction about Z axis. This is negative about first axis. Okay, that is there. Got it? So this is how it can move. That is the first axis. Now going to the second one. Second one is something like this. When you have second link which can rotate with respect to first link. So this is the reference marker. I have taken a video of that as well. Yes, you see how it can rotate. Got it? So this is how it can rotate. These are very closer picture. This is where you actually note that this is 0 degree. If it is matching one by one, okay, it is 0 degree. So there is direction convention that I will show you also. Okay, so now the axis which is third link moving with respect to the second one. So this is second, this is third. So this also can move with respect to this. Let me see if I have a video for that as well. Okay, yes, it is. So you see, is it not? So you see, it is moving.
Yes, sir.
Very good. So now let me go to the axis which is like this. So this is your third and this is your fourth link. With respect to the third, you see that was something around this direction. This is along a different direction, is it not? So this Z and this Z is directed in a different way. Okay, so this is your Z4, this was your Z3. Okay, so anyway, so this is your direction of rotation. Let me see, this is your marker for this. Okay, let me see again the video. Okay, so yes, this is it. Okay, so axis direction, you just notice the axis direction, and you also see U plus and U minus. Positive and negative is also marked here, is it not? So this is how it can rotate, correct? Okay, Okay. Now the other joint, yes. So now this is your fifth link. This was your fourth link, right? This was your fourth. Now it is the fifth one. Here is the marker. Another video now. Yes. So fifth link moving with respect to the fourth one, positive and negative. Got it? So this is how it is done. Done. Okay. Let me go back to this. Now the final one. So this is your sixth link. Sixth link is a combination of flange which can rotate plus the tool which is attached. In my case, I have a two-fingered gripper which is attached, and this was your fifth link. So fifth link, this is the sixth one. It can rotate. Here is the marker. It may not be that clear over here, but I hope it is more clear in case of video. So let me just run that one. Okay. So now you know how the sixth link can rotate with respect to the fifth one along with the gripper. So whenever the sixth link rotates, it rotates the tool along with it. Is it not? Positive and negative direction, both are there. Okay. So this is how. Okay. I hope it is quite clear how these robots are made and how different links are there. So this is your zeroth frame which is grouted to the ground using bolts. Zero, this is the first link. Okay, and then you have, this is your second link which can rotate with respect to the first one. So if this is the second one, you have the third one, third and fourth, fourth and fifth, fifth and sixth. So now hope you can understand different joint markers and different joint axes and their directions. Now let us see what is the way you are getting the angle. So every joint has encoder filtered at the top of it. So this was the actuator. Actuator has an encoder, okay, that gives me the angle. So each encoder is mounted on top of the joint itself, that precisely can give me the joint angles. Okay, so this was for the first one, this is for the second, this is for the third. So this is from the motor side of it. This is the fourth one. Fifth and sixth are embedded inside the structure of the robot. Casting, inside the casting it is there. Okay, it is not easily detachable. Yes, please. That I'll show you. I'll show you. Don't worry. So yes, hope you have got till here. So that is also marked. If you can see one of the video quite closely, hopefully it was here. No, not in this one. It is given in the manual also, but yes, I should show you here only. Yes, can you see this one? U plus and minus. That basically tells the direction of this. Can you see this clearly? U plus and U minus. So this is basically, it is marked, but yes, if this sticker goes wrong, that doesn't make you feel that you have lost it. There is manual to do this. Even the teach pendant, in teach pendant you move it in positive direction and see which direction it is rotating. With that also you can come to know. So basically in the manual it is marked like this. So this is how it is. Six different axes. All they call it S. Okay, L, that is the lower swing. This is swing. This is lower. This is upper joint. Okay, and then you have SLU, rotate, tilt, and some angle is there. Okay, so every robot, they have a different nomenclature for these joints. This is how it is given in the manual, which is positive, which is negative. Hope you got it this also. Okay, so now let me put the frames first, because what I want to do, I want to find out the end effector position. Over here it is not this position. I have a tool also. I want to know this position. I already know how much is this length. because that was my tool. I have calibrated it and I have found out, yes, this is almost around 235 mm. 235 mm is the length of my tool. 100 was from here. Anyway, so we'll see those dimensions later. First, I'll fix all the frames, how they should go. Okay. Okay, starting right from here, can I know where could be my z axis? Z0. This is if this is the center point of the base and this was your first motor, so yes, it should be something like this, so that this link rotates like this. Is it correct? So this becomes your first frame, that is the ground frame Z0. Okay, that is the one. Okay, so next will be look this very carefully. Okay, next joint is something like this. This should be my next Z1. This is your link 1. Okay, this is your link 0 fitted to the ground. This is your link 1 which rotates with respect to link 0. Okay, when actuator Z0 is active. Okay, and then you have Z1, that is the frame which is fitted at the end of link 1. We normally put, if this is link 1, so at the end you have frame 1. Okay, frame 1 is fitted at end of link 1. Okay, and it rotates with respect to the frame 0. Okay, that is how we'll go on. So this is your next frame. Z axis, let me just find out all the Z axis. Another Z could be, you see, this time U plus is like this and negative is like this. So this time your Z should be something like this. Is it not? This Z is something like this. Oh no, this is opposite. Okay, rather this will be opposite. Yes. So this Z, you see, this is L plus and L minus. So definitely this is your positive direction of Z1. Okay, so that when you do right hand thumb rule, this becomes your positive direction. Okay, so this is L plus, this is L minus, this is your Z1. In this case, you have Z which is something like this. So if you rotate this way, it is positive, this is negative. Is it not? So this is because this is link 2, this is your link 1, this is link 2. So what frame number will it have? This will have frame 2. So this is Z2. Okay, this is Z1, Z2, and then R plus. That means if this link can rotate, so this is your link. Link 3 was here. This is your link 4 which can rotate with respect to link 3. So you may have something like this. That is your new Z. Okay, about which you have positive direction like this, negative direction like this. So this Z direction is something like this. Again, you may have another Z which is something like this, because you have to make this as positive, right? So because this is positive, okay, so this is your positive direction of Z5, is it not? So Z5, and effectively final, if this is your plus, and last Z6 should be something like this. Okay, that is making this side positive and this side negative. Z6 is somewhere over here. Okay, so that is how all the Z will be placed. Now let us find out the joint offsets and twist angles. This is not complete, I am not yet done. Okay, yes. That is nomenclature basically. SUN, that is nomenclature. I can call it 1, 2, 3, 4, 5, 6. Done. Okay, that is as per Yaskawa, they call it SUN, RT, and so on and so forth. But yeah, Kuka may call it differently. ABB may have a different name. Doesn't matter. Yes, still you have any query here? Still you have any query? Okay, fine. So I can call it 1, 2, 3, 4, 5, 6. That is quite good enough to make me understand. Okay, and that is what I'll do now. Okay, so now let us begin with the first axis. Okay, with the physical robot, and I'll now won't call it UVW and so on like that. I'll call it 0, 1, 2, 3 like that. Okay, so now x-axis is normally placed in the positive direction of the robot, that is your physical x-axis. Okay, where you want, always forward is x-axis, z is the first revolute axis. Okay, first revolute axis about which your first link is rotating with respect to the ground link which is grouted to the ground. Okay, so this is your first link. Okay, so this becomes your theta 1, is it not? So this is your this. Now this point can be anywhere on this line because effect will be the same. You can either fit, because this is not moving, even the platform is not moving. So anywhere I have this rotation, this link will rotate, this axis will rotate about that by the same amount. Theta 1, it is rotation about z0 by an angle theta 1, and this frame location can be anywhere on this axis. Okay, so x0 can be here, x0 can be here, x0 can be anywhere. Okay, so normally we prefer basically Yaskawa they prefer it here, that is in the plane of this. In this plane they have put everything. Okay, so for no particular reason it is there, you can have it anyway. Okay, so that is to be noted. So let us first identify all the ds parameters here. Okay, so now do it once again. So let us say I have placed it anywhere I feel like. So the placement would affect the end effector position, because I am obtaining the end effector position with respect to this point. If I take it here, end effector position will be different. Okay, position vector will change. Even the orientation may change. If I have different orientation of x, that also can change. But normally that doesn't change. So yes, this has an effect. Okay, preferably placed on the floor where the robot is fixed. Okay, and z axis is always pointed about which the first link will rotate. So this is your first link, this is your z0, if this is your x0. Okay, now frame is used to locate the robot among set of other robots working together. So this is the position about which this robot itself is placed with respect to the universal frame, because you may have different robots in the workspace. Okay, first link moves with respect to this frame. Z0 may be placed anywhere along the axis of motion. For the time being, you let it be as it is. I'll explain you in much deeper later on. Okay, X0 is placed along positive workspace normally. So that is the reason it is placed like this. So now Y0 can be obtained as cross product using right-handed coordinate system RHS. Okay, so Z cross X. So which direction it should be? Like this, y0, is it not? So x cross y is z, is it not? So that is how you can obtain y0, but that is not very important. But at least for 0 you should know, because let us say you want to move along y0 axis, you should know where is your y0 axis, plus positive y0 or negative y0. So this is your ground frame, this is how I have placed. Okay, workpiece could be located, even the workpiece that you want to handle using robot, that also can be rotated, placed with respect to this frame. Okay, so that you can directly command the robot to go there and pick it up. Okay, so that should be doable. So this is how you place your frame 0. This is very, very important. Hope you have got it. If not, you just revise this video. Keep watching till you understand it. Okay, I am sure you will understand by looking at the statements which are written here, by drawing that I have done, and the text that I am speaking. Okay, So now the second frame. Okay. I have placed the axes as it is given in the manual for positive and negative direction. You can have your own frame. Any intermediate frame direction should not affect the end effector pose. Okay, as long as the end effector frame is placed in the same manner. Okay, now Z1. We have placed Z0 like this. So this is your Z1 because this was your positive direction of rotation as given in the manual. So this is your Z1. Okay, and it is always placed at the axis of rotation. So if this is your link 1, this was your link 0, this is your link 2 that rotates with respect to Z1. Link 2 rotates with respect to Z1. Okay. So that is there. So Z1 is located along axis of rotation of link 2. X1 is now common normal to Z0 and Z1. Z0, this is your Z0, this is your Z1. So this becomes your X1. Okay. So X1 is a common normal to Z0 and Z1 directed away from Z0. It is measured from Z0. Okay. So that is there. Why it is away from Z0 I have specifically mentioned, because here what will come is your offset and the link length. Okay. Will that be taken as negative or positive? It will all depend on that. Okay. Y1 is obtained using right-handed coordinate system, and that is not very important in any intermediate frames. Okay. So now distance measured along Z0 between X0 and X1. If this is X0, this is X1, distance moved along Z0, this distance is basically the offset D1. Okay, D1, this is the offset between two links. Okay, that is known as the link offset. So what is the link length? So distance measured along x1, okay, x1 is here, between z0 and z1, between z0 and z1, and it should move away from z0. That is your link length. If it moves away from z0 and x1 is directed like this, so this is your link length. So this is your link length measured as A1, and this is negative because it is measured from Z0 to Z1. X1 is directed opposite, so A1 is negative. So this is your first parameter table. So DI, if I take this frame over here, if this frame is over here, so DI becomes equal to 0. Normally it has some distance. As far as robot is constructed, there is always a distance over here. Okay, but Yaskawa takes it as 0 because rotating this anywhere on this is equivalent. So that is why it can't be taken as 0. We'll see how it affects the end effector position. Definitely orientation may not get affected that much. Okay, now what is alpha? So what is theta also? Theta 1 is rotation about Z0 axis. Okay, so it is something over here, that is theta 1. That is theta 1, and it is joint variable. This is joint variable. It is not a constant. So this is a variable. Now what is alpha? Alpha is joint, the angle measured along x1. So angle measured along x1 to bring z0 to z1. Z0 to Z1, you want to bring Z0 to Z1 by rotating about x-axis. So effectively it is 90 degrees. So that is the twist. So this is 90 degrees. So di theta a alpha. 4 parameters. One of them is joint variable. Okay, d theta a alpha. Hope you can see this. Okay, so d theta a alpha. This is the first parameter table, DH parameter table for the link 1, and we have already placed the frame 1. So this is your frame 1. This is your link 1. Frame 1 is placed and it moves along with link 1. It always moves along with link 1. Frame also rotates. Okay. Now talk about the second frame. How will I place that? I have already placed my,
Sir,
yes,
sir, why alpha is called as a twist angle?
it is called as a twist angle.
Is
It
there
has a
any
name
limit?
because link itself is twisted. You see, if this is the first axis, it is a good name which is given to match its functionality, is it not? A link is twisted means if at all you have a link which is not having a twist, both the axes will be parallel. Okay, if at all it is twisted, the axis about which it is rotating and the axis which it itself carries, okay, they have some angle between them. So that is why it is twist. Okay, so link is twisted, no, it is twisted. It has a literal sense also. Okay, anyway, you will come to know more better when you will actually see this. Okay, how two axes are placed. Okay, so angle between the first and the second was 90°. So forget about the first that we have placed. Now I have to place the link which is attached, frame which is attached to link 2, placing the second frame. This frame I have already placed. Okay, this frame I have already placed now. Okay, so this was placed. Now I want to put the other one. So this is your link 2, this is your link 2, frame 2 will be here, this is your frame 2. Now frame 2 should carry the z axis, Z2 axis that rotates the link 3. So link 3 gets rotated about Z2 axis. So Z2 is something like this. Okay, and again Z can be taken this side also or this side also, but because I know Z is the axis of rotation, positive direction has come from the manual which says this side is positive. I can safely keep it like this. Otherwise anyone can place it like this also, it is equally good. It won't affect the end effector position. Okay, so going with the manual I have placed it like this, and this axis was something like this. So this was Z1 about which link 2 is rotating. Okay, this is the Z1, so this is theta 1 about which link 2 can rotate. Now this will have rotation theta 2 about which link 3 can rotate. So this is your link 3. Okay, this can rotate. So this is your Z2. This is your Z2. Got it? So now I'll try to find out what should be my X2. X2 is common normal to Z1 and Z2. So this is the line that I have extended. Okay, so this is your X2. This is your X2. Got it? So I should not merge it with yellow line here. Let Z's B remain as red. Okay, so this is your X2 axis. Got it? So that is your X2, that is common normal to Z1 and Z2. Now the parameters. I have placed the frames, X2 and Z2 is placed. Y2 can be obtained by cross product, doesn't matter because this doesn't play any role in DS parameters. So I'll just skip this one. Now the distances. D2. D2 is the offset, distance measured uh, between two x-axis. Okay, that is always equal to 0. You see, this point and this point is on the same sagittal plane. Okay, and then there is no offset, there is no distance that moved along z-axis. Both are directly one over the other. So there is no offset. Got it? Both the frames are one over the other. So there is no distance. If at all this z I would have placed here, so this will become the offset. But that is not the case. Okay, so that offset is 0 here. Okay, so this is the distance, that may be 0, it may be non-zero, we'll talk about this later, but over here it is equal to 0. And now theta 2 is the joint angle that is measured between x1 and x2. If this is x2, okay, this was your x1, this was your x1. So x1 and x2, there is an angle. So this robot is already at a 90 degree. Okay, it already has that angle. Forget it. for the time being, that is a joint variable. Let it remain as theta 2, that is joint variable only. So it is just a variable, I have left it as it is, okay, but it is that angle. And A2 is measured along x2, and common normal between Z2 and Z1. Distance between Z2 and Z1, this is the distance, and what is that? That is link length 2, okay, and that is what is 2, okay. Now the twist is really a twist here, because you see positive direction of Z1 was something like this, positive direction of Z2 is something like this, both Z's are placed 180 degree apart. So this twist is something around 180 degree, okay, by the way it is, although they are parallel, but they are directed in a opposite direction, in the opposite direction. So that is why this 180 degree is here, okay. Hope you have got the sense of it. Basically they are parallel, but they are directed opposite to each other, and that is why it is 180 degree, okay. Okay, coming to the next frame. Again, this was your Z2, this was your link 2, this is your link 3, and I want to rotate link 3 about this. So this was your theta 2, forget it. Now I want to rotate fourth link with respect to this, but this can rotate about this, you know that about this is it was rotating, okay. So now it will direct like this, it will direct like this. So Z is something like this, Z3 is like this, okay, about which link 4 will rotate. Z3 is something like this, about which link 4 will rotate. It is placed at the end of link 3, but your shape may be something like this, doesn't matter, your axis is over here. It may or may not pass through the link itself, solid link itself, okay. So in this is the case with this. So effectively, when you take common normal between 2Z, this was your Z2, this was your Z3, common normal is something like this. So that will give you x3, and intersection point is over here, okay, and that is not lying on top of the link itself, okay. So that is where it is, virtually it is located there, and kinematically this is important, not the actual point of rotation where you want to place the, where you would love to place the frame, but actually it is not there, it is here, about this it is rotating, and effectively this link is rotating like this, okay. So yes, Z3 along the axis of rotation of link 4, common normal, x3 is common normal to Z2 and Z3, Z2 and Z3, Z2 and Z3, this is the common normal, this is x3, y3 as per RH coordinate system, right-handed coordinate system. Forget this. Now the distances. What is the offset? Offset D3. Again, both the points are one over the other. There is no offset, physical offset. So that becomes equal to 0. So D3 is equal to 0. Joint angle, this is theta 3. Okay, that is theta 3, and it is joint variable. Theta 3 is joint variable, it is not a constant. Okay, so that is theta 3 measured between x2 and x3. You have two x's, and A3 is measured along x3. A3 is the link length. A3 is the distance measured along x3. So this is your A3, okay, between Z2 and Z3. So if this is your Z2, this is your Z3, okay, you know that. So this is your A3, okay. And twist angle this time, if you measured along x3, so how much is that? That is again 90 degree, because first was something like this, another one is like this, angle between them is 90 degree. If you can see that clearly over here, angle between these two is 90 degree. So Z2 and Z3 rotated about x3 is 90 degrees. So that is your link twist. Exactly going by the definition. Don't go by its literal meaning. This can turn out to be link length. Sometimes it can be your offset, doesn't matter. As per definition of DH, distance between two Z is always link length and it will remain so. Okay, so that is there. So directly go by the definitions. Okay, follow this statements. So this is how you place the frame. This is how you find out the DH parameters. Okay, so this is your table till now. Now things will be little confusing now. Now you have to place the frame 4, frame 4, fourth frame. So that is, I prefer to put it here because this is your axis of rotation that was rotating this link. This is link 5. Okay, so link 5, this was link 4. So this is your Z4 about which link 5 will rotate. So this is your point and this is your direction of that axis. So that is quite clear. Okay, where will be your x4? X4 will be common normal to Z3 and Z4. This is your Z3. Okay, this is your Z4. So common normal is something like this. Common normal directed away from Z3. So it is something like this. It can again be placed this way also, but I prefer putting it this way. For any special reason, there is no special reason. You can put it otherwise, should work equally well. Okay, so I have put it this way. Okay, so this is your x4. Now that you already know x4 and z4, you can always find out where is your y4. Okay, so it is z cross x, z cross x, so y should be something like this. But that doesn't play any role, so I will wipe it off. So now that you have find out the frame, you have to find out the parameters, dh parameter. How it is done? D4 measured along Z3, okay, measured along Z3. There is no offset, okay, or there is some. Yes, there is some. If you measure from here to here, that is the distance along Z3. So this is the distance. So this is your offset. This time link length appeared like a offset because it is along z axis. It is not distance between z axis. If at all it is distance between z axis, it would have been called as link length, but now it is distance measured along z axis but in the negative direction. If z is like this, d is like this, so d4 is negative, which comes here, and this is your offset, not the link length. So that has come over here, offset. This was your link length. Link length is equal to 0. Why? Because there is no distance between z axis. If you extend it backward, it passes through z4. So there is no distance between z. Okay, that is what is making this as 0. Okay, and theta 4 is the axis about which it is rotating. So theta 4 is the joint angle measured between x3 and x4, x3 and x4, and that is a joint variable. So I forget it, I simply put it as variable. Okay, how much is the twist? So measured about x4, z3 to z4. You see it has rotated by an angle. So if this is your z3, this is your z4, this is your x4. So you have to rotate by an angle 90 degree to reach here. So that is why link twist is 90 degree. Okay, so that is what is making it 90 degree. And this is how the final fourth frame is placed, and that is here. Now you will see all the frames are intersecting and one over the other. Okay, let me just extend this one. Okay, I have just changed the color while I place. So this is the earlier frame which was here, fourth frame. I have just faded it off a bit. This one, this was your fourth one. Okay, fourth frame. Okay, and that was rotating the fifth link. So this is the fourth frame. Frame normally I denote it using hash symbol. So this was your fourth frame. Okay. So now I have to place the fifth frame. Fifth frame will rotate the sixth link. So where is the sixth link? This is the sixth link which is attached to this. Okay. So now direction of that, looking at the data sheet, this is something like this. This is your fifth frame that will rotate the sixth one. Okay, that will rotate the sixth link, and this is your direction of rotation. Okay, so again Z5 is along the axis of rotation link 6. Link 6 can rotate like this. So Z5 is something like this. Okay, and X5 is common normal to Z4 and Z5. If Z4 was something like this, earlier Z4 was here. Okay, if you remember, Z4 was something like this. Let me just show you once again. Z4 was here. I have just faded it here. So this was Z4. This is Z5. So effectively distance between those two, that is the common normal, is 0 now. Okay, distance, so that is making this distance equal to 0. Distance between Z4 and Z5, that is the link length 5, is equal to 0. Okay, and then there is no offset also. There is no, both the frames are placed one over the other, so there is no offset, so that is also 0, but there is some joint which is a variable, so that is theta phi. So this is theta phi. Okay, we don't bother about y now. Okay, so these are four parameters. Angle between Z5 and Z4 measured about this. So if this is your x5, measured about x5 going from Z4 to Z5, angle is 90 degree. So you have to rotate by 90 degree to go from Z4 to Z5. So that is your twist angle for theta phi. For 5 it is 90 degree. So this is how you keep moving, follow the rules, place the frames, okay, and find out the DH based on the rules. Go through this statement and what I am saying, follow the video, definitely you will understand. Look this once again till you get it. The final one now. So final one is just the dislocation of this frame, the fifth frame. Okay, I'll just wipe off everything now. In order to find, because the final frame, the sixth frame, is not having any other frames after that. Okay, so what I do, I don't know what should be the Z for this, because that is not carrying any further links. Okay, so I'll simply transform. So this was your fifth one. Okay, so this is your fifth frame. So I have just moved this to this location. So this is your sixth one. If this is your fifth one, okay, so this is your fifth link, this is your sixth frame. So let me just put the frames properly. So this is your sixth frame, this is your fifth frame. Got it? So I don't write it like this. Okay, so this is your fifth frame, this is your sixth frame. It is simply the replica of this. You just transform it here, do nothing, because it is not carrying anything. So it is assigned along Z5, common normal to Z's. You can common normal between Z5 and Z6. If this is Z6, this is your common normal, so this is your X6. You can find it, it can be other way, but I prefer it putting it in the same direction, so that you don't have to do any rotation, you just have to translate it from here to here. Okay, last frame includes the robot's tool flange distance. So this is your distance D6. Okay, effectively there is some distance between um, two x-axes. If this is x6, this is x5, distance between two x-axis along z. So if this is a distance measured along z, it will be offset. So it will come over here. This is the distance d6. So that is an offset, and it is measured along negative direction of z. So it is negative over here. Okay, and there is no rotation between z about x-axis, both the z as parallel. So that is what is making twist angle as 0 degree. Got it? So this is how the sixth frame is placed. So whole of the ds parameter table is now made. Okay, now you already know, now that we have reached, we have created the ds parameter table. So now I look at the physical distances as per the data sheet. So this figure I have obtained from the data sheet, and I can quickly relocate the distances which I have found out on the figure now. Okay, different frames. Okay, just a sec, let me just wipe me off. Okay, so this is your final location where you are, where you have reached, and this is your final frame. So this is your DH parameter table. I'll just see where are these distances. Like for distance D6, which you have seen just now, how much is that? I already know from the flange, this distance for me it was 235 mm. Okay, because this was the tool which was made by me. So this is, yes, this was 235, and from the data sheet, the flange, this distance from this is given as 100. If you can look carefully, you see this distance is 100 mm. From this point to end point, it is given as 100 mm. Hope you can see this carefully. Okay, very good. So this is your distance D6. Okay, last distance. Not actually D6. You have a tool that comes after it. Effectively, it is 235 mm. So effectively, I am at 335 mm from this point. Okay, and tool rotates along with the sixth link, so it doesn't matter. I can take them both together as 335. So this is first distance. Another distance which you can see. So yes, you see 450 mm. So this first point, no, this point where we have taken the first frame, it is actually at 450 from this. So this was your first offset D1. But now that if I place my first frame over here, okay, first frame 0 over here, so that becomes equal to 0. So everything, all the end effector position will be calculated with respect to this frame. Okay, but if I include this over here, D1, that is 450 mm over here, I'll get end effector with respect to the ground point. Okay, yes. So this is your first distance. Now 155 is your 155 is this distance. Where is that? You see, this is 155. Where is that? Let me wipe off a bit. That is distance from this to this point. Is it not? Distance between two z axes, that is the link length, and it was 155. If you can see here, it was minus of a1, so that makes it minus 155. So that parameter is taken from there. Similarly, the next one, 614, that is distance between this z and this z. Okay, that is 614. So that came here. Angles will remain the same because that is the structure of the robot. It is not going to change. This is the link length that I am obtaining from the data sheet. You can physically measure it. It is not that easy though, but data sheet tells it all. Okay, so this is 614. Now where is this 200? 200 is this. That is distance between this z and the z over here, this distance. Okay, so that comes over because distance between z is link length and it is equal to 200. It was negative, if you can see here, it was minus this, so it is minus this. Okay, now some other distances like 640, 640, that is distance between this point and this point. So that is 640, it comes here with a negative sign. 335, 235 plus 100, as I have said, this is D6. So that is D6. That comes here. So from the data sheet, I can quickly obtain this. Got it? So overall the DH parameter table is ready. Now how will I do this forward kinematics? I know d theta a alpha. So where were we actually? If you can see my first matrix, so this is your matrix. If you know your d, right, theta, a and alpha, alpha goes here, theta is here. So for each and every link you have a link transformation matrix that takes you from this point to this point. Okay, this is your link transformation matrix ai with respect to I minus 1. So if you can take product of all those, so that is where that is how we said we can do forward kinematics. So 0 to final point, you do 0 to 1, 1 to 2, 2 to 3. That means each DH, using each DH parameter table, you do find out this matrix, take the product and get the end effector position and orientation. Okay, this is what we intend to do. Okay, and this is how it is done. Now to so finally the frames were like this. Okay, understanding the current pose which it is shown here, at least you can directly sum how you can verify. At least this position is verifiable. You know this distance, this is 335, okay, and this was 640 as per the data sheet from here to here. So effectively at this point, this distance should be visible, 100 plus this, and then there is one more distance, that is 155. Okay, so 155 plus 640 plus 335 is 1130. That is this point's location with respect to this point along ground frame x0. Similarly, this is 0 because you don't see any motion along this y0, that is 0, and z you can simply keep on adding. So this is, if you take this point as ground reference frame, so this is 450 mm that will come, plus 614, that is this distance from distance to this, and then 200 which was here. So effectively it can be 814 mm, 814 mm from this point, okay, or it is 1264 from the ground point. So this is how it can be done. Okay, let us now quickly validate this using Matlab now. Okay, so these are the 2 points that I have done. These are the 2 points that I have recorded. Okay, so this is the first location, this is your second location. Okay, so now I'll just show you a small video how it was taken from the first one to the next one. So robot is taken from, this is your first location and this is your last location. For each of these position, I have noted down the parameters. What parameters? Basically this, joint angles. So this is a reset angle. For the current angle, it always shows as 0. For the home position, okay, for the home position it shows it as 0, okay, but for any other position it will say that as difference between this and that. Let us say if it is at this location and it was initially at this location, so all the angles were 0 over here, and next one will be simply a delta theta, that is change in angle. Okay, you can calculate the change in angle with respect to this home location, but I already know how much was my home angle, which was taken as 0 because I know my DH parameters. So angle between x axis measured about z is the angle. So at least for the joint, let us say one of the angle you can imagine. So if this is x0, this is x1, so initially angle between them is 0 degree. Okay, so already that angle is known. Okay, so similarly different angles can be known as well. Okay, so this is your 0, 0, 0 with the DH I can calculate how much is your 0, 0, 0. So whatever it shows for this position, I'll simply add it to this position and I'll get the angles for this location. Okay, if I know the angle, I can put them here, put them to my DH table. Okay, so I'll get d theta a alpha for all the length. I can calculate 0 to 1, 1 to 2, okay, 3 with respect to 2, 4 with respect to 3, 5 with respect to 4, and finally 6 with respect to 5. Take the product, you will get the, so using the link transformation matrix I minus 1, you can do this. Okay, take the product, you will get the end effector position. Okay, so that is what I'll do. So I have noted this initially, and the position was shown by the robot teach pendant. So this is from the teach pendant I have obtained, not directly available. I can go to software setting limit where it actually shows in degrees. Otherwise it shows me in pulse. So every number of tons, now you know what is a sensor. So number of pulse you can obtain. Okay, and now you can go get also understand the basics why it says the difference only, because they are encoder, maybe optical encoder or a resolver. It can just tell me the difference. So if it says the difference, mostly it says in terms of number of windows that it has counted. So it will just tell me the count using the incremental encoder. So that is converted to angles within the controller, but by default it shows me the counts over here in the software setting limit in the Yaskawa robot. It quickly can show you in terms of angle. So this is for the home position. This is the end effector position. For the end effector position is shown over here. So this is X, Y and Z. Roll, pitch and yaw is given. This is RPY. Okay. But normally in case of end effector pose, you can obtain the transformation in terms of, so what all things that a end effector transformation can show you. This three elements will show the position, whereas this 3 cross 3 matrix will show me the 3 cross 3 matrix will show me the orientation matrix, not the RPY, roll pitch yaw. So you need to have a converter which converts the NOA to equivalent normal, orthogonal and approach, as I have said, normal, orthogonal, approach, to RPY, roll, pitch and yaw Euler angle. Okay, so there is a conversion algorithm which is given in one of the data sheet which is here. You can quickly go there and you can find out this. This will discuss very much in detail in our own forward kinematics theory class. But for now, you take that as granted. Take that as I know already how to convert this 3 cross 3 rotation matrix to RPY, and I can validate this value to this one. If I do forward kinematics using this angle, home angle, I should get this position as this one. Okay, as it is shown over here in end effector pose, is it not? And this 3 cross 3 converted to RPY should show me this RPY. Okay, and similarly for the next position where it has reached after that, so this is the delta theta angle. This is not theta, this is delta theta from the home position. So this is how much the robot has rotated, and this is your new XYZ and RPY. Same you need to do here also. Okay, so now we'll do using simple transformation matrix using Matlab code. I'll just show you that now. Hope you can see this now. Okay, so now you can just notice this. What I have taken, this is a sample code I'll share with you. Okay, I'll give you an assignment also. So this is your D as per the parameter table. 0, 0, 0, minus 640. Let me just go to the parameter table once. Okay, let me just go to the parameter table once. So yes, So this is your parameter table, you can compare. Okay, so exactly matching d theta a alpha. Theta is joint variable, d a alpha. d a alpha is here, so it is exactly matching with this. So I will just substitute this here. Okay, I have just substituted it here, and this is your initial home position angle which is shown here. Okay, home position. Okay, and this is the delta theta which is there when you move from the home to the other position. This was your delta theta for different joints. Okay, so at least for the first one I'll show you here. So this is your delta theta. Okay, I have added it to theta 1, that is the home position angle. I have added the delta theta to get the new theta, and I have just used a transformation matrix which is nothing but link transformation matrix coded over here. Okay, so if you convert this link transformation matrix, so I'll just take product of all those transformation matrix. Okay, product of all those transformation matrix from 1 to 6, and I can obtain the end effector position for both the locations. So let me just do it. So this is what it gives me. So for the first point, it gives me this. Okay, and this is your matrix basically. Can be, just let me just run once again. Okay, so this is what it is. Okay, so this 3 cross 3 is basically orientation. Okay, and then this is your end effector position, and effectively this should be shown. And then for the second point, this is your end effector position and orientation. So 802 471 minus 34, let me see if it compares to the actual thing that I have obtained here. Okay, so it is almost matching. So you see it is 801.9 471.34. So that is the position. So that is the position. Okay, let me see what Matlab has given me. So it has given me 802 point something, 471 and 34, almost matching. So this is your end effector position. Similarly for the home one, 1130, 0 and 814, and exactly that should be there in case of teach pendant what it shows. This was for the state 2, this is for the state 1. It is 1130, 0, 814. So exactly that one. So you see, this is as per the teach pendant what I have obtained, and with the my own forward kinematics that you have learned just now, you can do it. So I'll share you this code. Okay, this is just two examples when two different states are compared with my forward kinematics algorithm. Okay, and I could do it. I want you to do it now with the given data set. Okay, what is that data set? I'll show you now. Okay, so I'll share you with this one. Okay, I'll share you this code. Yes, exactly this angle and end effector position I'll share with you. What it has, it will have joint theta angle. Okay, it will show you this for different delta theta. Okay, different delta theta, this is angle. You have to calculate the end effector position and compare with this. So this is your xyz, which is shown here, is it not? Or I have done it almost for 5 different positions. So I will give you 5 different angular delta theta. You have to add it to the initial home position angle. I'll share you that. Okay, so this is your joint angle, and this will be your end effector position. Okay, so just put these angle, create a table of all these 5 readings. Okay, I have done it for 2 states. I'll share you some 5 state reading. Okay, put the joint angles, get the end effector position and orientation. Okay, so this file I'll share with you all. Okay, and that is what you have to submit as an assignment. Okay. So yes, that's all. So yes, thanks a lot.